Welcome back. In our earlier days in algebra, we used coordinate systems to analyze scalar quantities. In vector analysis, we also need coordinate systems. So in this module, we're going to discuss the different coordinate systems such as Cartesian coordinates, cylindrical coordinates, and spherical coordinates, and how it applies in vector analysis. Um, we'll also take up how do we transform from one coordinate system to the other. Let's start by discussing Cartesian coordinate system. So sometimes this is also called the rectangular coordinate system. So let's say we have a point P in space and we want to locate that point in space relative to some other point O called the origin. So we need to specify three things: the x coordinate, the y coordinate, and the z coordinate. Now this point can also be considered to be the intersection of three planes. We have the x equals x sub 1 plane, the y equals y sub 1 plane, and the z equals z sub 1 plane. Let's say at this point P, we're trying to measure the wind velocity. And let's represent that velocity by the vector a sub rect. Now that vector a sub rect can be represented by the sum of two vector components in the Cartesian coordinate system. That is, a sub rect is actually the sum of a sub x vector ax plus a sub y vector ay and uh, a sub z vector az, where a sub x, that component, a sub y, and a sub z are the component vectors of a sub rect in the direction of a sub x, vector ay, and vector az respectively. But what are these vectors represented by the small letter a? So we call them the unit vectors because these are vectors having a magnitude of 1, and these are their directions. So a sub x is actually perpendicular to the x equals x sub 1 plane, and it lies on the surface of z equals z sub 1 and y equals y sub 1 planes. A sub y, the unit vector a sub y, is normal to the y equals y sub 1 plane and also lies on x equals x sub 1 and z equals z sub 1 planes. And a sub z is also normal to z equals z sub 1 plane and lying on the planes x equals x sub 1 and y equals y sub 1 planes. So all of these unit vectors are perpendicular with each other and all have a magnitude of 1.
So when we express a vector in this manner, what we really mean is we're trying to express the vector as the components, as its component along the axis of the coordinate system. So this one is along the x-axis, this one is the vector along the y-axis, and this one is a vector along the z-axis. So we sum the three component vectors and that will give us the original vector. And because of that, take note that we could also express the vector in this manner, where this one is the magnitude of the vector and this one is a unit vector which has a direction the same as the original vector. Take note that this unit vector should also satisfy this expression, which is again the sum of three component vectors. And because this is a unit vector, this one must be equals to unity.
Let's say we have a point in space with a given coordinates, and let's say we connect an arrow from the origin going to that point. The vector created by doing so is called the position vector. Um, with the length of that arrow as the magnitude of the vector, and the direction is from the origin going to that point. Now, in that case, if we express it in terms of its component vectors, it becomes that each of the components has a magnitude the same as the numerical value of the coordinates, as shown here. Uh, and the magnitude of the position vector should be given by its um, Pythagorean um equivalent, as shown here. And the unit vector corresponding to the direction of that vector should be given by this expression. So the unit vector is the vector itself divided by the magnitude of that vector. Let's say we have 2 points in space, P and Q. And along with those points, we have two position vectors, R sub P and R sub Q. And we want to know the vector from point P to point Q. Then all we need to do is simply get the difference RQ minus RP, or ROQ minus the vector from origin to point P. To prove this, take note that this is like adding the vector RP and the negative, or the vector RQ, and the negative of vector RP. So if we draw this, let's say we have vector RQ. So this is RQ, and we add to this vector the negative of vector RP. So that will be the opposite of this vector. So we add that vector, and we get the sum of this vector. So this is RP negative, and we get the sum of these vectors. So we'll get this vector. So this is RPQ. And you'll notice that this vector is really the same as this vector. And to express the answer in terms of its component vectors, we do this. So the x component is simply the difference of the coordinates. The y components is also the difference of the coordinates, and the z components as well is the difference of the z components, or the z coordinates of the two position vectors. And to get the opposite distance vector from point Q to P, we simply get the difference, uh, vector RQ or vector RP minus the vector RQ. And again, to express it in terms of its component vectors, uh, we simply get the difference of their coordinates. And to get the unit vector of a distance vector, that is a vector with a magnitude of 1 and the same direction as the distance vector, we simply divide the vector itself by the magnitude of that vector, where the magnitude of the vector given by this one. Let's say we have two vectors expressed as its component vectors. To get their sum, a plus b, we simply add their components. So we add the x component, the y component, and the z components. To subtract the vectors, we simply get the difference of their components. So we get the difference of their x components, the difference of their y components, and the difference of their z components. Let's go to the multiplication of vectors expressed as their component vectors. So let's say we get the dot product A dot B, where the two vectors are expressed as their component vectors. That would be given by this expression. So we simply add the product of their components. Take note that this is also equals to the magnitude of A times the magnitude of the vector B times the cosine of the angle, the smaller angle between them. Okay. Now to get the cross product of the vectors given as their component vectors, we can use this determinant. Again, take note that this is equals to a vector whose magnitude is given by this, okay, and that vector is perpendicular to the plane of created by these two vectors. So let's say these are the two vectors and we get the cross product. What we get is a third vector. So that is directed. So this is the two vectors. It is perpendicular to the plane created by these two vectors. And the magnitude of this is equals to this. Now, again, take note also that the magnitude of this third vector as a result of the cross product would be the area of the parallelogram created by the two original vectors. So this area. Let's say we have two vectors, A and B, and we want to know the projection of vector A along vector B. So we could either get the what we call the scalar component. So the scalar component along B is just the projection of A. So this length. Now that length, we call that the scalar component of A along B, and that would be given by this expression. So it's simply the magnitude of vector A times the magnitude of the unit vector that has the same direction as vector B. So this is the unit vector that has the same direction as vector B times the cosine of the angle between the vector A and that unit vector, or the angle between the vector A and vector B. Or simply that would be the dot product of A and the unit vector A sub B. The other component is called the vector component. So if we want to get the vector component of A along B, so that would be this arrow. So we just take this result and associate with that the unit vector B. Okay, so this one is simply this, and we associate the unit vector AB, or that can be written as this one. We have touched previously on vector fields, and in the context of the coordinate system, so let's say we have the coordinate system here. We said that a, a vector is a field because at any point that vector can have different directions and magnitude. Okay, um, if the vectors all have the same magnitude and direction, regardless of their location, we call that vector a constant or a uniform vector field. Um, so that would be seen as having a component that are constant. So in this case, vector A is a vector field that is constant or uniform, also the same as here in vector B. If these components happen to be functions of their coordinates, then that would not be a constant or a uniform vector field. On our next video, I will give a few examples to give a clear picture of what we have discussed so far that pertains to the coordinate system. So I'll see you in the next video.